Hello. Last time we have discussed the time-dependent Schrödinger's equation for a free particle, and it's time to move on and include a potential in which a particle finds itself. So we will generalize the time-dependent Schrödinger's equation in this way. Also, we will introduce the time-independent Schrödinger's equation, which allows you to calculate the energies of a particle which is not free, which is confined, for example, an electron in a hydrogen atom. I will introduce the concepts of quantum numbers, energy levels, and degeneracy of energy levels. Then I will not solve the time-independent Schrödinger's equation for hydrogen, but I will tell you the main results of that solution. Also, I will introduce the concept of spin, which is the internal angular momentum of all elementary particles except for Higgs boson. Higgs boson have spin 0. And finally, I will give you a calculation of degeneracy of the energy levels in hydrogen. So without further ado, let us refresh our memory about the main steps to derive the time-dependent Schrödinger's equation for a free particle. We realized that the energy is represented by an operator, which is the partial time derivative multiplied with I imaginary unit and reduced Planck's constant h bar. Momentum is represented by an operator, which is the gradient operator, nabla, whose it is a vector operator whose all three components are the partial derivatives with respect to the three Cartesian coordinates d by dx, d by dy, d by dz. And in the momentum operator, the gradient is multiplied with the negative imaginary unit and Planck's constant h bar. Then kinetic energy operator is obtained by recalling the classical mechanics expression for the kinetic energy, momentum squared divided by twice the mass. And the square of momentum operator is just apply momentum operator twice. All right. All right. So it's more precisely, it is a dot product of the momentum operator with itself. Okay. So a dot product of the gradient operator with itself is the Laplacian, the sum of the second derivatives with respect to the x, y, and z coordinates. And for kinetic energy, you need to multiply the Laplacian with negative h bar squared over 2m. So having written down all these expressions for the operators, energy, momentum, and the kinetic energy, we can formulate the time-dependent Schrödinger's equation for a free particle, which says that the energy operator and the kinetic energy operator acting on the wave function must give you the same result, because all energy of a free particle is its kinetic energy. Now it's a simple further step to include an external potential in which the particle finds itself. You simply add, so in the right-hand side of the time-dependent Schrödinger's equation, you have kinetic energy. All you need to do is to include the potential energy, which is given by the product of the potential energy V of R, potential energy function, with the wave function of the particle. So the total energy represented by the operator I h bar d by dt is the sum of the kinetic energy and the potential energy. So that's our time-dependent Schrödinger's equation for a particle in a potential. Next, so if the potential is confining, actually it doesn't need to be confining. So for any potential, you can write there are special states, special wave functions, which have the property that they correspond to stationary probability density. The probability density in those special states is the probability density is a function of position, but not a function of time. So modulo squared of the wave function does not depend on time, even though it may depend on the position r. Such states are called stationary states. To obtain a stationary state, the time dependence in a stationary state must enter in a specific way in the form of exponential to the power negative I times angular frequency omega times time t, and then angular frequency is the ratio of energy to Planck's constant, so exponential to the power negative I energy time divided by the reduced Planck's constant h bar. The time independence of the probability density in a stationary state follows from the fact that exponential raised to the power imaginary unit times any number, any real valued number, has unit modulus. Now, the function that multiplies the exponential is the position-dependent, time-independent wave function. And the probability density in the stationary state is modulo squared of this position-dependent, time-independent prefactor of the exponential, which I denote as capital psi. So that the probability density is capital psi of r modulo squared. All right, now if you take the partial time derivative of a stationary state wave function, then since your prefactor capital psi of r does not depend on time, you only need to differentiate the exponential. And the derivative of the exponential is just the product of this exponential times whatever multiplies the time argument in the exponential. That is negative I energy E divided by h bar. Like this. Now, recalling the time-dependent Schrödinger's equation here, I h bar d psi by dt, multiply the time derivative with I h bar, you'll find that energy times the wave function in the stationary state is minus h bar squared over 2m Laplacian of the time independent part of the wave function, capital psi. So this is the kinetic energy in the stationary state, plus the potential energy function times capital psi. And you can take the exponential, the time-dependent exponential outside of the brackets. Finally, you can cancel out the time-dependent exponentials in both sides, and you arrive at the time-independent Schrödinger's equation for a single particle in a potential V of r. It says that the total energy here, E is not an operator, it is a number, some number. The total energy is the sum of the kinetic energy, which is the first term, and the potential energy, which is the second term in the right-hand side of the time-independent Schrödinger's equation. Right. Now, solving the time-independent Schrödinger's equation is not always easy. Most of the time, it is difficult. It can be solved relatively easily for a particle in a square well potential. That is, the potential energy is 0 inside some domain and infinite outside of that domain. It can be solved for a parabolic potential. It can be solved for hydrogen atom. But for arbitrary potential, it can be solved only numerically. So you would need to write a computer code to solve it. But it is all doable. And once you solve the time-dependent Schrödinger's equation, you will find that the solutions, the wave functions that satisfy the time-independent Schrödinger's equation depend on a set of quantum numbers. which I denote collectively as alpha. And alpha is actually a collection of several quantum numbers, alpha 1, alpha 2, and so forth, which label the quantum states and the respective energies E alpha. So psi alpha quantum states, stationary quantum states, and the energies, energy spectrum, E alpha. Now, how many quantum numbers are there? Well, that depends on the nature of your system, but the number of these quantum numbers does not exceed the dimensionality of the problem. So, for example, in 3 dimensions, the number of these quantum numbers cannot be bigger than 3. In 2 dimensions on a plane, it cannot be bigger than 2. And in 1 dimension, it is just one quantum number. So you cannot have 0 quantum numbers. You need at least 1. The range of these quantum numbers depends on the potential V of R. We will discuss specific examples later, but okay, actually, let's discuss one specific example that you are already familiar with. A free particle, so the potential is 0. A free particle has the wave function in the form of a plane wave, e to the power I kr minus omega t. The time-independent part of this wave function is just exponential to the power ikr with the normalization factor 1 over L to the power 3/2. So, and I would like to remind you that we pretend that our electron, our particle, finds itself in a cube, in a very big cube of side length L, and we impose periodic boundary conditions. So the normalization of the wave function is 1 over L to the power 3/2. So the integral of this wave function modulo squared over the whole volume of this cube is 1. The quantum numbers on which this wave function depends are the components of the wave vector k. And because the particle is in 3 dimensions, there are 3 those components, kx, ky, and kz, 3 quantum numbers. If the particle were not in a cube, but were performing a 2-dimensional motion inside the square well, with side length L, with periodic boundary conditions, then there would be 2 components of the vector k. All right. Now, this solution perfectly illustrates the concept of degeneracy. The energy in the state characterized by the wave vector k is h bar squared times the magnitude squared of the vector k divided by 2m. You can have many possible values of the wave vector k whose magnitude squared is the same. And this is the concept of degeneracy. So degeneracy is not something unusual in real life. Like if you have a rock, a macroscopic object, a rock, and it moves with of mass 1 kilogram, and it moves with the velocity 1 meter per second, then its kinetic energy is 1 times 1 squared divided by 2, half a joule, no matter in which direction the rock is moving. Degeneracy is the situation when the energy in a particular energy level can be obtained as many combinations of the quantum numbers. So you can have many combinations, for example, of the x, y, and z components of the wave vector k, which correspond to the same energy E. All right, so degeneracy is more precisely, degeneracy is the number of quantum states that correspond to the same energy. The quantum numbers label quantum states. Quantum states each quantum state is described by its own private, distinct wave function, but it may happen that several quantum states have the same energy. The quantum states that have the same energy are said to belong to the same energy level. And if a particular energy level has more than one quantum state, this energy level is said to be degenerate. All right, next. I am not going to solve Schrödinger's equation, time-independent Schrödinger's equation for an electron in a hydrogen atom. But here is this Schrödinger's equation: kinetic energy and the potential Coulomb energy of interaction between the electron and a stationary nucleus in the center of hydrogen atom and in the center of our coordinate system. Let me just say that solving this equation is possible, even though its solution would take probably one full lecture. The quantum numbers that characterize this solution, there are three of them. They are denoted with the letters N, L, and M. This M should not be confused with this M, which is the mass of the electron. Unfortunately, Latin alphabet has only 26 letters, and sometimes you have to use the same letter to denote different things. So this M is a quantum number. This M is the mass of the electron. Now, the names of these quantum numbers. The number N is called the principal quantum number, and it turns out that the energy in the state characterized by the numbers N, L, and M depends only on the principal quantum number N. And it depends in exactly the same way as predicted by Bohr's simplified Bohr's theory of hydrogen atom. That is negative Rydberg's constant, 13.605 electron volts divided by N squared, principal quantum number squared. The principal quantum number can assume values 1, 2, 3, and so forth. So the energy in the ground state, in the lowest energy state is called the ground state. So the energy in the ground state of hydrogen is negative 13.6 electron volts. The energy in the next excited state corresponds to N equals 2, and it is negative 13.6 divided by 2 squared. So divided by 4, then 13.6, negative 13.6 divided by 9, and so forth. Next, we have orbital quantum number L. The orbital quantum number defines the magnitude of the orbital angular momentum of the electron as it orbits around the nucleus. Right? So orbital motion means if the electron somehow rotates around the nucleus, very, 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 very loosely speaking, an electron is rotating around the nucleus, then there must be, it has an orbital angular momentum. So the magnitude of that orbital angular momentum is determined by the orbital quantum number, and it turns out that the orbital quantum number changes between 0 and the principal quantum number minus 1. So in the ground state, when N equals 1, principal quantum number is 1, ground state, lowest energy state, the orbital quantum number has only one value, which is 0. So no angular momentum. But if the orbital quantum number is not 0, well, for any value of the orbital quantum number, the magnitude of the angular momentum is reduced Planck's constant, h bar, times square root of this orbital quantum number times orbital quantum number plus 1. Yes, notice that the Planck's constant, which is measured in joule seconds, in C units, has also the units of orbital angular momentum. Yes, angular momentum units, because joule is Newton. Well, because joule second can be expressed as meter, as kilogram meter squared per second. Yes, joule is kilogram meter squared per second squared times seconds, so kilogram meter squared per second. Angular momentum units. Okay, finally, the magnetic quantum number m, which characterizes the solution of the Schrödinger's equation, assumes the values from negative L to positive L, increasing by 1. So negative L plus 1, negative L plus 2, ta, 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 0, 1, 2, 3, ta, 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 L minus 2, L minus 1, L. In total, it can assume 2L plus 1 values. So if L equals 0, then M can assume only one value, which is 0. If L equals 1, then M can assume the values negative 1, 0, and positive 1, 2L plus 1 values, and so forth. And it is called the magnetic quantum number. It determines so if the electron is somehow orbiting around the nucleus, it has angular momentum, but it turns out that only one component of angular momentum is a vector, which has three components, x, y, z. And it turns out that only one component of the angular momentum can be measured. And by convention, it is taken to be the z component. The x and y components are undefined. We know that they add up with the z components in such a way that the total angular momentum must have a specific value, but the x and y components are not well-defined quantities. So the z component of the angular momentum is the product of the orbit of the magnetic quantum number and Planck's constant h bar. All right, so these are the hydrogen quantum numbers. Like I said, I will not be solving hydrogen Schrödinger's equation, but I need you to remember to keep in mind these quantum numbers because we will need them in the future. Then there is a further quantum number, which is not captured by the time-independent Schrödinger's equation. This quantum number is associated with some sort of an internal degree of freedom of the particle, and it is called spin. Very, very, very loosely speaking, you can think of an electron as maybe a little ball which rotates around its axis. But this is a very inaccurate picture because an electron is not a point particle which is localized in space. You cannot say where the electron is. It is spread out in space. So it is not a little bullet or a little ball. It's not. It's spread out in space. Yet it does have this internal degree of freedom called spin, and the internal motion, the internal degree of freedom of the electron does not appear in the time-independent or time-dependent Schrödinger's equation unless electric field is switched on, or unless you want to take into account such fine effects as spin-orbit coupling. But we will not do that. We will just keep in mind that electrons have spin. And now, actually, there is the spin quantum number emerges in a very natural way if you try to combine Schrödinger's equation with special relativity, as done by Paul Dirac, the English physicist, Paul Dirac, who formulated the relativistic version of the Schrödinger's equation called Dirac equation. And so if you merge special relativity with quantum mechanics, you end up with this Dirac equation. And it follows from Dirac equation and also from experimental observations like Stern-Gerlach experiment that the spin of an electron can have only two values. The z components, the projection of the spin on a particular axis, the z axis, can have only two values. And those two values are either positive half or negative 1/2 of Planck's reduced Planck's constant h bar. So electrons are said to be spin 1/2 particles. And there is a whole bunch of other elementary particles which are spin 1/2 particles. They are found in the standard model, such as quarks, the particles which make up protons and neutrons. Then we have muons, tau leptons, which are the fundamental leptons in standard model, neutrinos, which are the partner particles of the leptons. They are all spin 1/2 particles. There are also particles in which spin is integer. Typically it is, so for example, the particles which are responsible for interaction, they have spin 1. So the most common type of interaction, the most familiar to you interaction, is the electromagnetic interaction. And at the most fundamental level, electromagnetic interaction proceeds via exchange of photons, the quanta of light. But also there are other types of interaction, strong interaction and weak interaction, and they are mediated by particles called gluons for strong interaction and particles called W and Z bosons for weak interaction, and all particles which mediate interaction, electromagnetic, photons, strong interaction, gluons, weak interaction, W and Z bosons. All of them have spin 1. There is yet another fundamental particle from standard model which is responsible for the mass of some of these particles, in particular for the mass of the weak W and Z bosons. And this is the Higgs boson. The Higgs boson has spin 0. It is the only spinless zero spin particle in the standard model. And you probably have heard about such particles which called gravitons, which may or may not exist. We do not know yet. No? But if they exist, then they should have spin 2. All right, and so all those particles which mediate interactions have integer spins. All right. And here is the final slide about degeneracy. And I would like to give you another example of degeneracy. This is the degeneracy of hydrogen energy levels. I said before that degeneracy is a situation when several quantum states, more than one quantum state, have the same energy. So a particular energy level has same energy, but many different more than one different quantum states that belong to that energy level. And the degree of degeneracy is the number of those quantum states that have the same energy. In the future, for the sake of brevity, I will just use the word degeneracy instead of degree of degeneracy, because we now all know what degeneracy is, right? So I will just use the word degeneracy instead of degree of degeneracy. So let us calculate the degeneracy of an electron in a hydrogen atom. So the quantum states of an electron in hydrogen are characterized by 3 quantum numbers, actually 4 quantum numbers now, 4 quantum numbers, which are the principal quantum number n, the orbital quantum number L, the magnetic quantum number m, and the spin quantum number s. So electron can be either spin up or spin down. The energy depends only on the principal quantum number n. and it is negative Rydberg's constant times the square of the principal quantum number, which can assume values 1, 2, 3, and so forth. The orbital quantum number changes from 0 to n minus 1, so it can assume n different values. The magnetic quantum number changes from negative L to positive L, so it can assume 2L plus 1 different values. And the spin quantum number can assume the values either positive or negative 1/2. So in order to figure out the degeneracy of the energy level n in hydrogen, we need to calculate the number of combinations of all quantum numbers except for the principal quantum number, which correspond to the same principal quantum number. So let's do that. The degeneracy will be denoted with the letter G. Subscript n, Gn, means degeneracy of the energy level n. And it is given by the by the sum over all those three quantum numbers that we have: orbital, spin, magnetic. So spin quantum number can assume the values negative 1/2, positive 1/2. So this sum has only two terms. Then we have another sum over the orbital quantum number, which changes in the range from 0 to n minus 1, so n different values. And then we have the magnetic quantum number, which changes in the range from negative L to L. Every time one of these three quantum numbers changes, we need to add the number 1 to the total degeneracy. So the summand is just the number 1. All right. Summation over the spin can be performed easily because the rest of the sum does whatever is inside this of this external sum over the spin does not depend on the spin quantum number. So the external sum over the spin has just the value 2. So 2, this comes from spin. Then we have sum over L, sum over M of this number 1. All right. Next, we calculate the internal sum over M, the magnetic quantum number. Magnetic quantum number can assume 2L plus 1 different values. So here we go, 2L plus 1. So what remains is to take the sum of this 2L plus 1 over L from 0 to n minus 1. And we recognize that this is the arithmetic series expression. And just a reminder, if you have arithmetic series, so each next term is bigger than the previous term by a fixed amount, then the sum of arithmetic series is the first term plus the last term divided by 2. So this is the average value of a single term in the series. First one plus the last one divided by 2, the average, multiplied with the total number of terms in the sum. And if you apply this philosophy, this approach to evaluate the sum of this 2L plus 1 of this arithmetic series, you will get in the end that the arithmetic series has the value n squared, the principal quantum number squared. So this means that the degeneracy of the ground state in hydrogen, ground state means n equals 1. The degeneracy of that state is 2. The electron can exist in the state with spin up or spin down, but its orbital angular momentum and has the value 0. The degeneracy of the first excited state, n equals 1, is not n equals 1, n equals 2. The first excited state, n equals 2. This is 8. The next excited state, n equals 3, has the degeneracy 18, and so forth. All right, so that's so how to understand, for example, the degeneracy 8 of the first excited state, n equals 2. Well, 8 is 2 times 4. 2 comes from spin. 4 comes from so 4 comes from the orbital motion. You can have either the orbital quantum number equals 0, in which case the magnetic quantum number can only have the value 0, or you can have the orbital quantum number equal 1, in which case the magnetic quantum number is either -1 or 0 or +1, so 3 states. 3 plus 1, total 4 states, multiplied by 2 due to spin, so that gives you 8. I believe this is the last slide, and I wish to thank you all for your kind attention. See you soon.